So, hi everybody. It's good to see you back after a few months that we were on a break. So we resume our seminar about MIP star is equal to RE. And the first two talks will be given by Alon Dogon and Danil Akhtiamov. And they will talk about the connection between Cohn's embedding conjecture and Kirchberg's QWEP conjecture. Alon is starting, so Alon, the floor is yours.
Okay, thank you, Michael, for the kind introduction and the second opportunity to talk here. Great, so as Michael said, we will today talk about the relation between Tsirelson's problem and a certain conjecture of Kirchberg's. Before I start, I wanted just to remark that this talk will be kind of a bit different from what we had last semester, in the sense that will be slightly more mathematically oriented. So complexity theory won't really play a role here. However, Tsirelson's problem is something that actually I think all of us have seen, because there aren't so many new members. But part of the talk is kind of to remind you of the question we had there. So let me start gently. You see my screen, right?
Yes.
Great. So what is the goal of this talk? The goal is to, as the title suggests, connect Tsirelson's problem with Kirchberg's QWEP conjecture. And this, in turn, will relate the study of quantum correlations arising from different mathematical models, like the tensor product model and the quantum commuting model, with the study of C-star algebras. And the latter one is what I refer to here as kind of a deep mathematical theory that doesn't seem on paper to have some, one would expect a relation, but it's nice and surprising that there is actually a direct relation between these two topics. And of course, this in turn gives a direct relation between Tsirelson's problem and Cohn's embedding problem. Now, the Cohn's embedding problem is a problem that Michal presented relatively even early on in the seminar, but it was also a bit hard to formulate, and we didn't. We saw some hints towards. Actually, we saw theorems that really relate Tsirelson's problem and Cohn's embedding problem. However, this time we will take kind of a indirect approach in relating them, in the sense that Cohn's embedding conjecture is actually equivalent to Kirchberg's QWEP conjecture, and both conjectures come from a field called operator algebras. Although these two conjectures have different, on paper, quite different formulations, and they are talking about different objects. However, it's an important result that they are actually equivalent. So the relation we give here actually indirectly gives a relation between Tsirelson's problem and Cohn's embedding problem. Now, in order to establish this relation, we will need to introduce two exciting objects. One of them are tensor products of C-star algebras, and the second one is universal group C-star algebras. And there are quite a lot of subtle questions about them, which are in nature quite reminiscent of the Tsirelson's problem, the philosophy behind it. But let's begin with really reminding what are the objects we talk about coming from quantum information theory. So fixing notation, I will denote by gamma, just a pair of integers, where k you should think of as the number of questions and m is the number of answers. And we will refer to gamma as a Bell scenario. This might be a kind of a strange name for a simple object, but just gamma, a Bell scenario is just a specification of the number of inputs an experiment has and the number of possible outputs. Now we want to define our first correlation set, which will be denoted by Q tensor product of gamma. This will turn out to be just a subset of a k squared times m squared dimensional Euclidean space. And it denotes the set of correlations arising from tensor product models of arbitrary separable Hilbert spaces for Alice and Bob with the number of questions and answers specified by gamma. Okay, this was kind of informally what it means, but now let's recall the formal definition. So recall that a POVM is a collection PI, say, I from 1 to n, of operators in some Hilbert space, BH. So this is a Hilbert space. Okay, such that PI are positive, so positive in the sense of operators, and they sum up to the identity. So this was like already seen quite a lot in this seminar, but just my personal take on it. If you haven't seen such a thing, you can interpret this as some non-commutative analog of simply a probability vector, right? Because if PIs were scalars, then this would just mean a probability vector. But here we are taking positive operators on a Hilbert space, so positive matrices which do not necessarily commute. But this is like the right formulation for probability vectors in our setting. And then what is PABXY? So given a 2, so given, let's start from one collection, a collection of POVMs for Bob, for Alice, actually. So how I'll denote it? I'll denote it P, and here X and A, okay? Where X runs over questions. So what do I mean a collection of POVMs for Alice? You should think of, for each fixed X, running over A gives you a POVM, okay? So I would ask for something like P, where summing over A should give you the identity. And, but I choose for each question a independent POVM, and this should be a POVMs for Alice on a Hilbert space. HA, okay? So what we will see as kind of characteristic of this type of correlations is that each one of the players has their own Hilbert space. This will be somehow not true in the second correlation set we define, but really here we think of everyone's data as living on some separate Hilbert space, except for the state, which we will mention later. And in the same way, Bob gets a set P of Y and B, where now Y runs over questions on some Hilbert space HB. Okay, so Bob has a separate Hilbert space. Now, in order really to capture the phenomena of entanglement, we take a state C, which will be a unit vector inside HA tensor product with HB. So the tensor product of Hilbert spaces was a certain way of getting a new Hilbert space out of two of them, which you can mix stuff together from the both of them. And this C is exactly something like that. So C is a unit vector. And now the fundamental formula of the type of correlations we consider here is that given, so XY denote questions here, right? So these are questions and these are answers. So this is basically should be in your head. The probability of getting the answers A and B respectively for Alice and Bob, given that they are given that they got the questions X and Y, this should be the inner product formula of taking psi and the image of psi under the tensor product of the POVMs evaluated on psi, okay, with this inner product. And indeed, you can check that this, given every x and y, summing over a, b, this becomes 1, so that this is indeed the, we can interpret this as some condition, probability distribution given x, y. Yeah, are there any questions about this model?
Can I ask a general question?
Yeah.
We are studying two players, Alice and Bob.
Mm-hmm.
So my question is, why two? I understand that one is not interesting,
Mm-hmm.
but is three somehow can be solved using two, or is two just the first interesting case, or is two more interesting than any other number?
No, so you certainly can. And what we will do, I think what we will do now, basically you can extend it. I mean, the whole, it's actually a good question. I mean, I'm thinking of it in terms of the end product of like the question about tensor products. And indeed, I don't think everything should, like every statement you ask about these situations should reduce to two-player cases, but I really am not an expert, at least on the quantum information side, so I may be wrong. But certainly on the side of C-star algebras, I mean, you can also mix, you can, I could see the potential of mixing the models in case of, like, for example, you could have two players with a tensor product decomposition and the third player only commuting or something like that. But certainly, I mean, when you take more than three, I think you can ask even harder questions. But
okay.
That's just my guess. I don't have a complete answer. Oops, I left the slide. You still see my screen, right?
Yeah.
Okay. Okay, so now let me
following up on Guy's question, is it conceivable that there is something here like a number on the forehead model?
Sorry, again?
As in in communication complexity, there is something called the number on the forehead model, where everyone is aware of all the inputs except one. And that somehow is more interesting than everyone has one input.
Yeah, but you'll have to require, of course, the commutation.
Okay.
Yeah. So I confess I'm less familiar with like more general questions. I'm just aware that they exist. But I'm sure that probably you can give better answers for different ones. But I mean, I will say that the things that the techniques and dictionaries we develop here, they are quite general, and like you certainly can use this for more than one player, more than two players. It shouldn't be a problem. But okay, what the next correlation set, which I guess you also heard about already, is we want a more general model of modeling, like, okay, I didn't say at the beginning, but what are the point of these correlations is to kind of model the distributions of experiments who are spatially separated but may have quantum entanglement, and we model it on the basic idea of getting like inputs and outputs. But for this lecture, we will only be interested in the correlations. Like, you might remember that from the previous semester, we mostly talk about games, right? Where we also have a verification procedure, and then we interpreted the correlations as strategies for players. But here we will somehow, the games or the linear functionals won't play such an important role. We will mostly be interested in the correlations themselves. Did someone want to ask something? Okay. So what is this model? Let me recall it quickly. So now we are given two POVMs, collections of POVMs. So we have how did I denote it before? XA. XA. Yes, sorry, I should use it AXA. That's much better. Thank you, Michael. And we have BYB. So these are each, for each question, this is again a POVM, but now on the same Hilbert space, on H. Okay, now we don't have HA and HB. We have a single Hilbert space. This is the biggest difference, such that we need a commutation relation that AXA, the commutator of AXA and BYB, should be trivial for any quadruple of such questions and answers. Okay, so like this commutation relation is necessary in order for what I will define to actually be a probability correlation. And indeed, we define here P. Okay, so before we do that, and now our state Psi is in our single Hilbert space H, and the correlation is defined by the similar formula, just that now we simply multiply them and don't take tensor products. This will be the fundamental formula for quantum commuting correlations. And indeed, you can already see that this model is more general, because if we took, okay, now imagine you had PAX, PXA, and PYD from before on HA, HB, okay? So now we would define the tensor product POVM, or just take AXA to be PAX tensored with the identity on HB, right? And similarly, BYB will be the identity on HA tensored with PYB. Okay, so that these two, you can indeed check that they are still POVMs, but now on the tensor product Hilbert space. H will now be the tensor product of both of them. And we translate it from one model to the other, right? These guys will commute. Okay, so in general, QC gamma will contain Q tensor product of gamma. These are just two ways of that are mathematically sound of modeling experiments. Now, the natural question is whether one is stronger than the other, right? You could ask whether they are strictly equal. And this is exactly the content of Tsirelson's problem. But let me, before moving forward, just mention that Hilbert spaces we consider here are infinite dimensional in general, right? Separable, because in the case where, okay, let me state the problem and then explain why it's important. The problem is that whether it's true that for any Bell scenario gamma, so a specification of questions and answers, the closure of these tensor product correlations is exactly all of the quantum commuting correlations. Now, let me remark that you could also ask, okay, whether they are strictly equal, like, but we actually ask a more difficult question here, whether you can approximate things here by convex sums from here, kind of. And it's indeed justifiable to do this because we will see today that this is closed and convex. Convex. Okay, both are subsets of Euclidean space. However, it's not so clear. It's quite clear that they are convex. because there are probability correlations. However, both of these differ already in the fact that it's not easy, but we will do it today to prove that in the quantum commuting model, limits of correlations also arise from these commuting QWEPs, which is already non-trivial. However, it wasn't clear, at least, whether this correlation set is closed. And indeed, it was proved by Slofstra very recently, but before MIP star equals RE, that indeed this thing is not closed. So this was already refuted, but this stronger question, this harder question was refuted only once the MIP star equals RE paper came out. Okay, and this was like the strongest form of Tsirelson's problem, and of course we ask it for any type. Like we ask whether this is true for any number of questions and answers, like, because we might see also that, for example, for the Bell scenario, gamma equals 2, so only 2 questions and 2 answers. So you think of, for example, the CHSH game, where you only have 2 inputs and 2 outputs. These guys actually coincide. I mean, there you cannot find separation. However, the paper of MIP star equals RE, as Michael explained last semester, actually refutes this in showing that in general, there are some Km for which there is an inequality. Okay, so is Tsirelson's problem more or less okay now? And this is the kind of the thing that we talked about last semester. And now I will move on to something that we haven't talked about much.
Alon, I forgot, what's so presented this way, what are the K and the M for which this is known to be wrong?
So this is so at least
10 to the 20.
10 to the 20.
Yeah, mute let's.
I just said 10 to the 20 also.
Can you say in one sentence where do these numbers come from? Like very, very quickly, just the accumulation of how
the construction. Yeah, the construction of the game. If you unravel it and try to ask at the end how many, like the actual game that separates between the left set here and the right set here. So it's some functional. How many questions and answers are there? So they did only a back of the envelope calculation, as I understand, and reached about 10 to the 20. Like this is what they say.
This uncompressing the compression.
Yeah, but for a specific game, like they have a specific construction. You should think of their specific construction as prove to me that you have entanglement of 2 qubits, and then prove to me that you can win the same game that I just mentioned when I compress it. Okay, so this is a specific game, and they show that this game shows a separation between these 2 sets, and they can, using back of the envelope estimations, say that it consists of at most 10 to the 20 questions and answers or so, something like that.
And do we know that 5
like
is
it's an upper? I think they did like they say that it's an upper bound, clearly not.
No, so
like
do
they
we know that
estimated
5
some
is
upper
not
bound.
enough, Michael?
I'm not sure what is the least number that we don't know of. Like I know that the separation from Slofstra, you can estimate what is like. There are no numbers of when the lower this. I'll try to annotate. Just a moment.
No, but Michael, this is not what I'm asking you. I'm asking, do we know that this statement is, so if I limit K and M to be up to 10, do we know that the statement holds?
I didn't understand the
No,
question. Say again, or maybe Michael just answer.
Nati, I don't. I'm not sure, but 2-2 we know, but I don't think we know 3-3.
Exactly. Yes. Like, and it will be nice. For example, we will deduce 2-2 here from the fact that, I mean, for every, okay, you might ask me, why am I denoting this by gamma? And the question, the answer is that it will turn out that we will define a group that has parameters with respect to K and M. And specifically with 2-2, this group will be amenable. And as a result, the equality will hold. However, like for our other parameters, it will be non-amenable. And then it again becomes this hard question. So you will see like what I mean later, but I guess, yeah, I'm not sure whether it's known for other parameters, whether there's other example of parameters, whether there's equality. I think it's very interesting, but I don't know about it. Okay, so I think I'll continue. Now we really, before I launch into the preliminaries, I wanted to just let you appreciate the elegance of the Kirchberg's QWEP conjecture, because it consists of a single equation, right? We don't have K, M, we don't have like this specification of parameters. We simply ask for an equality of two objects, one being what's called the maximal tensor product of the free group algebra, and the second one being the minimal tensor product. And the goal of this lecture will be to explain what both of these guys mean, and probably we will explain what this means next time. But without further ado, let's start doing that. Okay, so we did talk about C-star algebras last semester, but I will not assume it and present C-star algebras on a budget. So what is the definition I'll use here? So a C-star algebra is a unital closed. So when I say closed, I mean closed with respect to the operator norm on BH. And so C-star algebra it contains the unit. It is topologically closed in the norm topology, and it is a star subalgebra of BH. So when I say star subalgebra, I mean if an operator is inside this algebra, then so should its adjoint be inside. Okay, and this in some sense inherits most of the structure of BH, and this is why they are kind of amenable to some methods of kind of infinite dimensional linear algebra. But for the sake of brevity, I won't dwell on this definition too much and just give some very trivial examples. The first one is, of course, BH, as it's a C-star algebra. It's a subalgebra of itself. In particular, matrix algebras are finite dimensional C-star algebras, right? And the second example is maybe a bit more interesting. Actually, it will be interesting because it will be directly related to our story. You can consider the vector space of dimension M over C as the subalgebra of diagonal matrices inside M and C, right? And what's special about this is, okay, first of all, it's finite dimensional. I mean, here this can be infinite dimensional, of course, and it's commutative, right? Multiplying diagonal matrices is basically like pointwise multiplication on C to the M. So this is, again, a very easy example. There are many more, but I won't get into them too much. And now I wanted to recall what is the natural morphisms.
Can you spend a second and open a window towards a more interesting example, something?
Yeah, so for example, so let's expand on the commutative examples a little bit more. Say X is a compact metric space. Okay, you can then consider Cx, which is the functions f from x to the complex numbers, which are continuous. And this has like a natural algebra structure, right? Which you might even encounter in second-year calculus courses in the Stone-Weierstrass theorem. And it has a norm, right? It has the supermum norm, which in this case is just a maximum. And I claim that this is in fact a C-star algebra. Now, it maybe is a little takes a little bit of thought to understand why it's a C-star algebra in the definition I gave here. This is because you can let C of X act on, okay, maybe I'll zoom in a bit so that you see a little better. You can let C of X act on an L2 space, L2 of X with some measure mu. Maybe I'll denote it in a superscript. And here mu is a fully supported measure. Okay, so once you choose a fully supported measure on a compact metric space, which you can realize this algebra as an algebra of multiplication operators on this L2, on this vector space, right? I just take for example, a continuous function. I take a vector C and I define the action to be simply multiplication. This will define a natural, in more mathematical language, a faithful representation of this algebra on this Hilbert space. And you can check that it is norm closed, and the norm is exactly the supermum norm, so that this also constitutes of a family of examples of C-star algebras. In fact, there is actually, last time I talked about it a bit, an axiomatic definition of a C-star algebra, of like what the star algebra structure, the norm structure, and how they should interact with each other. But this axiomatic definition turns out to be absolutely equivalent to the definition I gave here in what's called the Gelfand-Naimark-Segal theorem, which says that any such algebra which satisfies this list of axioms can be realized as such a star subalgebra of BH. But here you already see that kind of topologies in some, one can prove that this CX, the structure of CX, remembers completely the space you started with, so that C-star algebras kind of extend the theory of topology in some sense. But these are like the only, we will see the most important example, the C-star of F2, I think next week, which will be a very important example and very interesting. It will be an example that somehow encapsulates all the representation theory of F2, but that will be for next time. And for now, I really need you to believe me that these objects are worth talking about.
Alon, let me maybe mention another good example. If you can just take the closure of some operators. And the important case here is, I mentioned it in the talk I gave in Alex's seminar, is that if you take the elements of the POVM of one of the players, for example, you can just take the C-star closure of it, and you get an important C-star algebra, which has relations to the game that you are actually interested in. So there is a way to, if you are given a strategy for a game, interpret it as some C-star algebra, which already sits inside some B of H. And we saw in my talk in Alex's seminar that properties of this algebra are related to properties of the game. So this is another very, like, you construct the C-star algebra from a finite set of matrices or operators.
By the way, this gives rise again to a metric space and a measure, a fully supported measure. The example.
So actually not. This was exactly the point I mentioned at the beginning of the fact that POVMs are already non-commutative objects in general, right? Because all the algebras CX are commutative. in fact, if you have a C-star algebra which is commutative, then it will be of this form as you expected. However, the algebras in general, like passing from classical to quantum, so for example, POVMs, these will already define non-commutative algebras. So you can't really realize them as points of some space. So you really need to talk about the algebras themselves. And indeed, like as Michael mentioned, the case of taking a POVM and then it's the C-star algebra generated by it is particularly fruitful because we will also, like, this will be part of how we translate from building correlations to building certain maps between C-star algebras. Like, it will be also made clearer, hopefully next week. And I'm doing this also because, like, last semester we did talk about this relation. So it's more important for me this time actually to talk to you about more of the mathematical theory of C-star algebras without too much reference to as to why they are interesting. And you will see it very clearly next week, hopefully also this week. It will already be reminiscent of Tsirelson's problem in some sense. But okay, if there are no, hopefully that cleared things up. But now just to continue with the mathematical theory, we want to define maps between C-star algebras. So the first natural definition is that if you are given two of them, A and B, a linear map, so maybe I'll switch to a highlighter so that it won't confuse you. So a map here, pi from A to B, is called a star homomorphism if it is multiplicative and it preserves the adjoint and also preserves the unit. Okay, now you might be asking me, Alon, you're forgetting something here. What about the norm structure, right? I didn't say anything about C-star algebras were required to be closed in the operator norm topology. So obviously it's part of the structure we're considering here. However, it is like a theorem that a star homomorphisms are contractive. So in fact, once you have such a map, it will be true that pi of A, the operator norm, will only be smaller, just from the algebraic definition. And as a result, if you have two algebras that are isomorphic algebraically, then their norms coincide, right? But this is like one of the features of this theory, that there are some automatic analytic properties from algebraic properties. But okay, that was like the natural definition of morphisms between algebras. But we will need for our dictionary a much more general definition of a map between two algebras. So this is what is called a UCP map, which also played a role last time, but we recall it here. So given a C-star algebra A and then a map from A to BH. So here I don't take B, but I just think of the codomain as just all of BH for simplicity, is called a unit or completely positive map, so UCP for short, if there is a Hilbert space H hat together with an isometric embedding of H inside H hat, so H hat is a larger Hilbert space, and we are guaranteed a star homomorphism pi from A to B H hat. So I'll delete this so it will be clear that this is H hat, such that we have the following compression form. So before I interpret this, let me mention that PH is I denote here, like you have H inside H hat, and PH is the orthogonal projection, PH. And what does this formula mean? It says evaluate pi of A, so this will be an operator inside the larger Hilbert space, right? And then kind of restrict and compress it to our smaller Hilbert space. Now, this may be a bit I saw some people that this might have confused them at first. Like you might ask me, like, what is the difference? Now the difference is that well, what did you say?
The difference between what? I didn't
Between
understand.
star homomorphisms and UCPs. Like, it seems like I didn't do much to pi, right? Like I took pi to BH hat and then compressed it. You might, for example, wonder whether phi of A is also a star homomorphism. But in general, it is not. It will be a star homomorphism when pH commutes with pi A, meaning that H, the thing here is that H is not necessarily pi invariant. Okay? Picture the following situation. Say you're given a star homomorphism pi from A to BH hat, and I simply choose some subspace H of H hat, which is invariant under the operators of pi, all of them. Then for all considerations, I can just think of my pi as valued inside BH, right? Because I can just think of these operators only acting on H. And that would indeed give me a star homomorphism, but here, like in general, PH is not necessarily an invariant subspace. So when you do this compression, you kind of ruin the multiplicativity condition of a star homomorphism, right? Like phi of A, B is not necessarily equal to phi of A times phi of B, because you have this projection in the middle. And so UCP maps are kind of a generalization of star homomorphisms. Yeah, I mean, okay, this definition maybe seems a bit arbitrary to you now, and not necessarily we will actually do a proof that involves this. We might just take it, most of the time we will state theorems about UCP maps without proving it. But this is like the simplest definition that I can actually give you now without it seeming too mysterious. And of course, like some of you may know that this is not the usual definition of UCP maps. There's a slightly more complicated definition that looks more like positive definite functions. But for now, just think of these UCP maps as a generalization of star homomorphisms between C-star algebras. Okay, are there any?
Can you give maybe a very simple example of a UCP that's not a homomorphism? Do you have one?
Yeah, okay, there's an example, but it won't be very clear that it is UCP. The fact that it is UCP, you might see only later. But if you take, for example, CX, so the example of that Nati liked, and you think of a probability measure mu, okay? Mu, a probability measure on X. Then the function taking f from Cx to the integral of f with respect to mu, which is a complex number. So BH here will be just the complex numbers. This turns out to be a UCP map. Although like it's very clear that it's not multiplicative, right? The integration is not multiplicative. However, it turns out that you can indeed realize it as some compression of a representation on a larger Hilbert space, not just C. This is exactly the GNS construction, but we will see that later. But if you want an example, this is an example which is clearly not a star homomorphism. It's just also not clear it's UCP.
Expectation, right?
Sorry?
This
Yeah,
is
the expectation. Exactly. Yeah. So actually, if you, thank you. So I'll continue now with a proof, with a statement and then a proof, and then we'll switch to Danil. But now I want to talk a bit more about like the example I gave for a UCP map, which is what's called a state on a C-star algebra. And and this will play a central role in our dictionary. So what is the definition? A state on a C-star algebra A is a linear functional, first and foremost, rho from A to C. So it's linear, but it's not necessarily multiplicative. And the only condition we impose on it is, again, a positivity condition. And yes. And what do I mean by positive? I mean that rho evaluated on operators of the form A star A will be positive for any A coming from the algebra. And second of all, I want it to be normalized in the sense that it evaluated on the identity will give you 1.
Should be rho,
Okay.
not phi.
Sorry. Thank you, Dorit. Okay, so indeed, like the previous thing I gave of taking a function in the algebra of continuous functions and integrating it with respect to a probability measure, this is a state, right? Because a probability measure evaluates to be a positive number on positive functions, and also it's normalized, right? So this is indeed some would say a non-commutative analog of a probability measure, but here's the formal definition. And just like probability measures, we would consider the set of all of them on a certain algebra. So this math script of A will denote the set of states on the algebra, which will be a subspace of the dual space of A as just a normed space. So there's a hidden statement here that says that the operator norm of a state will always also be less than 1. So it will be contracted. In fact, if you think for a second, if you believed me that rho will be UCP, then you see that it must be contractive, right? Because a UCP is a composition of a star homomorphism, which is contractive, together with a compression operation, which is also contractive in nature, right? So states are in fact a convex closed subset of the unit pole of the dual space, and thus they are compact in the weak star topology. Now it won't play a very central role, but we'll see it later. In case you haven't seen what is the weak star topology, but here is like a central proposition, which we'll use later. So let's see be a C-star algebra represented on the Hilbert space H, and let rho be a state on it. Then I want to say that this state can be approximated by convex sums of vector states. So what do I mean by that? I say that for any finite set of elements inside your algebra, C, and every threshold epsilon you choose, I can find coefficients for a convex sum so that there are positive coefficients which sum up to the 1, and a finite set of vectors in the Hilbert space such that rho will be approximated by this convex sum, evaluated on xi. Okay? So the game here is you give me a finite set of elements of the algebra and a threshold epsilon. I guarantee you that I can approximate arbitrarily well rho evaluated on this finite set of elements using vector states. So what I refer to as a vector state is a functional of the form taking an operator x and evaluating it like this. And yeah, is the statement of the theorem clear? Okay, now I want to prove this, but I warn you that the proof is heavily functional analytic. So if you haven't seen some functional analysis, don't be discouraged. Okay, so what is the first reduction we say?
Well,
is that every...
Alon, I don't know if this helps anyone, but this is really the infinite dimensional cousin of SVD decomposition, singular value decomposition.
Yeah, singular value decomposition
and
of
even,
a...
of the, even simpler than that, of the spectral theorem. you know, you have to pay your dues to the gods, and you don't make equality, make them sufficient as arbitrarily close to equal, but it's not much more than that. I mean, everything else that we agree, I'm assuming, I didn't see the proof yet, but my feeling is that this is all you do. You take the proof of the spectral theorem on you know, real symmetric matrices, and you do some adaptations. And but I may be wrong, but that would be my guess. The way it looks.
This is the feeling of all this C-star algebra until the point where something doesn't work, and then it becomes extremely hard. So we will see today when it becomes hard, because like,
okay, so in other words,
like
my
the QWEP conjecture is again.
We're still in the plain. We haven't gone to the mountains yet.
Yeah, so I personally have to say I don't see exactly how you would. Maybe you could utilize the spectral decompositions of xi's, but I think something that you need to like internalize here is that we are not approximating an operator or a set of commuting operators, but we are approximating a linear functional on operators. So it's kind of, it's still a bit different in my opinion, but I'm just maybe missing the exact perspective you have on the statement, but kind of the non-triviality here is that rho we define to be an abstract thing on the algebras and functional with the positivity condition, and suddenly we can approximate it using objects that are dependent on the Hilbert space, right? These vector states. But if you want to explain to me later how you see it in finite dimensions, I would be happy to listen. But for now, let's really launch into the proof. And I think that even for finite dimensions, this is quite different from the proof of the spectral theorem. So again, we are given xi's and epsilon and rho. This is our input. And the first thing I say is that you may assume xi are self-adjoint. Why is that? Because each operator decomposes as two self-adjoint operators, and the approximation statement is rho and these vector states are all linear, so we can replace them with approximate each part separately. Now we did that in order to pass to a real vector space. The space will just be a finite dimensional space, actually, of the span of the unit together with our finite list of self-adjoint operators. Now we kind of want to formalize the translation of positive functionals on this subspace versus positive functionals on the whole monstrous algebra C. So we can think of, okay, so what I call the closed convex subcone S plus of S are just operate elements which are positive in the C-star algebra C, which are contained in S. So this is a subcone of S. And every state rho on the algebra restricts to an element of the dual cone of this S plus. So by dual cone, I mean linear functionals on S which are positive on this cone S plus. Conversely, every element of this dual cone, so a positive linear functional on S, can be extended to a multiple of a state on C by the Hahn-Banach theorem. So the whole point in this paragraph is to localize our proof to just, I don't know, you have a monster C and we find some two-dimensional subspace inside it. And now we only talk about somehow positive functionals on this subspace. Okay, because every positive functional on this subspace can be extended to a positive functional on the whole space by the Hahn-Banach theorem in a certain non-trivial way, but I'll leave that as it is. Okay, so now we want to do some separation. So what is actually our statement? Our statement only involved xi's, and notice that every vector state certainly also is like in the dual cone S plus star. So it restricts to a positive functional on S. And hence all the convex sums, this forms a convex subcone of S plus star. Okay, so pictographically, now it's really in finite dimensional spaces. You can think of some cone. This is S plus star. And then we have some subcone. Here, maybe which is this, which consists of these things. I want to note it. And our question is whether this subcone is dense, right? Because we exactly wanted to approximate every positive functional on S by such convex sums, right? We only considered xi's, so we can restrict ourselves to this finite dimensional subspace. So now we assume by contradiction that this subcone is not dense in S plus star. So choose a point. So we can assume that this is closed also, we close it off, but there is some point rho. Now points in our cones are functionals, right? Because we're talking about dual cones. So there's a state rho, which is not in this closure of these guys. By again by the by the geometric Hahn-Banach theorem or the Hahn-Banach separation theorem, we can find now a codimension 1 subspace in S dual, which separates this point rho from the subcone, right? But we know that finite dimensional spaces are reflexive. They are canonically identified with their double dual. So in fact, the Hahn-Banach theorem here guarantees, so I'll highlight what is the important part here. This gives an element X of S, which is a real linear combination of xi's that evaluates to be positive on all such vector states. However, there is some point rho, which is exactly this point we chose outside of the subcone, which evaluates to be negative, right? Because this canonical isomorphism between S and its double dual is exactly kind of by evaluation functions. So finding an element of S dual which separates is actually finding an element of S which separates this dual, these functionals. But this is a stark contradiction, right? Because X X here will be self-adjoint because it's a real combination of the xi's, which are all self-adjoint. And also, it evaluates to be positive under vector states, right? But this is exactly the definition of a positive operator. So X is positive. However, like we were guaranteed a state rho on C, which evaluates to be negative on it. Okay, so this proof is
You were cut off. We
more
can't.
functional, is a bit
Alon, you were cut off.
large. The general idea is okay. You can't hear me? Wait a second.
Now we can
Can
hear
anyone
you.
hear me?
Yeah.
Sorry, where was I?
Yeah, not so.
Did I finish the proof, say?
Yes, you did.
Okay.
But
so do you have any questions? Yeah.
I have a comment. If you can go back before the proof. But before it. Yeah, so just for the physicists in the audience, to give some dual way of looking at this. So this is called a state because basically you can look at a density matrix, that is a Hermitian matrix, positive semi-definite trace 1 matrix, which corresponds to a quantum state, as a functional like that, which takes operators to their expected value, physical expected value, which is just the trace of the state, the row, times A, times this operator, the observable. So you can view a quantum state as a functional from a matrix to the complex numbers. And then if you're talking about finite Hilbert spaces, then it's just like Nati said, just diagonalize this Hermitian matrix and write it as a sum of projectors on its eigenvectors. Right, so row will just be a sum of the eigenvalues of the projectors on each eigenvector. So okay, this the complexity comes from the fact that we're working over infinite Hilbert spaces, right?
Sorry, so Dorit, yeah, so forget about the infinity of the dimension. So, okay, rho is the sum of projections with weights. So what next?
So the proposition.
The operator A, the one.
So
yeah, like as Dorit said, like when, sorry, I'll try to say if I understood you.
Just write rho as a sum of lambda I of its eigenvectors, okay? Xi I, projector on xi I.
Yeah.
And then rho, trace of rho of an observable, trace rho x, if x is a matrix, is equal to the sum of lambda I, the sandwich of xi A xi.
Right, yeah, good.
So this is some kind of a generalization. I'm not sure exactly how general. I mean, it's just generalizes in the direction of the Hilbert space being infinite, right? This is.
Yes, I mean, for finite dimensions, your argument works very well. Even also for other infinite dimensional C-star algebras, which are called Tracial von Neumann algebras, your argument works.
Right.
But this is like in the most general setting, which we will need actually, because our algebra will be extremely infinite dimensional. So this is needed. In some sense, the infinite dimensionality of it is the result of MIP star only. But okay, I think this was, so we have two proofs, at least for the finite dimensional case. And now I will let Danil continue from here.
If I understand correctly, what when Alon mentioned this von Neumann algebras is that sometimes you can diagonalize the operators and use like the ones with the most weight on the diagonal, even if it is infinite dimensional. But again, even this argument doesn't work always, right?
It works because the trace gives you a pairing between the between the pre-dual and the between trace class operators and the states on the algebra. But yeah, you need a faithful trace to do this.
Thank you, Alon. Okay. What Alon just said was about approximating an arbitrary state using linear combinations of the states of a very simple specific form, and it was kind of complicated and required some inequality with epsilon because we didn't want to change the Hilbert space. We had some fixed Hilbert space. But if we just fix a state and are allowed to run over all possible representations, then we get a much cleaner statement, which is the following. It basically says that if we are allowed to run over all possible representations, then any state is just of this very simple form.
What does GNS stand for?
Gelfand-Neymark-Segal construction. Okay. Now in the form.
Danil, go back for the previous slide. I need a moment to digest.
So can you remind what a cyclic vector is?
I'm not sure it really matters for the purpose of the talk, but it's just a vector such that if we start acting on it by the representation and consider the span of like all the emergent vectors, we get a dense subspace of HV. Okay.
So again, I have to say, to translate to the physicist, this is the purification. This is basically extending the Hilbert space to a larger Hilbert space so that everything looks like a pure state.
You can move on, Danil. I digested.
So now in the formulation of the QWEP conjecture, we had some tensor products. So let's discuss tensor products now. So if we have two sister algebras, we would like to define the tensor product. But the problem is there is no canonical way to do so, because there are at least two possible ways. There are at least two possible natural ways, which are in general different. And the problem with the tensor product of sister algebras is actually that sister algebra has to be norm complete by definition, while the most natural construction we can give, which is just the algebraic tensor product, gives a non-complete algebra. So let's discuss the algebraic tensor product first. If we have two sister algebras, they are first of all some vector spaces by definition. So we can just we can just take their tensor product as of vector spaces as a base vector space for the algebra, and we can define the multiplication structure and the involution structure in the most natural way. And the only problem with this construction is that it is not complete. Not only it is not complete, we didn't even specify any normal representation or whatever. So to make it a sister algebra, we should define a norm in it. But before moving to defining the norm, let's discuss in a more abstract manner what an algebraic tensor product of algebras is. Yeah, actually, it has the following universal property. In this universal property, actually, it does not matter that A and B are sister algebras. It would work for any just what is called star algebras, and these are it's almost the same as star algebras, but like the crucial difference is they do not have to be, they don't have to have any norm and don't have to be complete, like no norm. And in such a situation, we also have star homomorphisms, which have to just respect the structure. And the universal property in this case of the algebraic tensor product would be the following. First of all, if we have if we have any star homomorphisms from A to C and from B to C, where C is any star algebra, then it like if we have any star homomorphism from any star algebra C such that their ranges commute, then it gives then it can be extended to a star homomorphism from the algebraic product to C, and vice versa. If we have a star homomorphism from the algebraic tensor product to C, it gives us some pi A and pi B with commuting ranges. Any questions? Okay, let's move on.
So what is this pi? Okay, pi is just apply pi A to the A part, pi B to the B part, and multiply, and you're using the commutativity.
Yeah. If you want to see the actual the actual construction, then if you want to recover pi from pi A, pi B, then you just do it like this.
What do you mean when you say pi A and pi B commute?
Like pi A and pi B commute for any A small and B small.
Okay.
I mean, it's also I should have said that it's a very reasonable requirement, because if we have such a P, then like pi of A tensor B can be written as this on the one hand. On the other hand, it can be written like this also. Which gives
Yeah, I think the important point is that the embedding of A and B inside the algebraic tensor product is such that the image of A and the image of B inside the algebraic tensor product are commuting. So it must be, for you to have some kind of this universal property, you must have this property preserved by pi A and pi B. And this is what Danil just showed, like algebraically in the last row.
Actually, what I just said is actually more or less the same as when Alon explained why the quantum spatial model is a particular case of the quantum commuting model. Okay. So as I said, it's a perfect construction, but the only problem that that we did not define any norm. So we would like to consider what is called C-star norms, because these are norms in which we can just take a completion afterwards, and what we will get will be a C-star algebra. So, and here you can see a definition of what a C-star norm means, and like again, it's a very reasonable definition, because at least because it's certainly satisfied for algebras and for subalgebras of operator algebras, of the algebras of operators on the Hilbert space. So what we are gonna do now is we are gonna build two different norms on the algebraic tensor product satisfying these two properties.
Is a 2 exponent 2, which is redundant, right? In the second, the norm of A star A is the norm of A squared, right?
Yeah. Wait,
yeah, that's a mistake.
Yeah. Yeah, thank you. Okay. So let's first define what is called the minimal norm.
So you're referring to the axiomatic way to define sister algebras, right? Rather than the sub-star algebra, closed unital sub-star algebra that we saw at the beginning.
Like I'm not exactly referring it in the sense we just will skip the corresponding technical details, technical proofs, I guess. But the idea, like for if we did those proofs, we would have to use the axiomatic definition of sister algebras. Yes. But it won't appear because these details actually are not that interesting. So the first way to define the norm is first we consider some representations for A and B in the algebras of bounded operators. And here we have that A acts on HA, B acts on HB. So after we considered the algebraic tensor product, it acts on the tensor product of the corresponding Hilbert spaces, and it gives us an embedding of the algebraic tensor product to the algebra of bounded operators. And now we can just consider the norm on the algebraic tensor product induced from this algebra of the bounded operators on the tensor product of the Hilbert spaces. This will be called the minimal norm, and the corresponding norm closure will be called the minimal tensor product. And it is not that easy, but also is not that hard to prove that the isomorphism class of the minimal tensor product actually does not depend on the chosen representations. Okay, any questions? Okay.
Can you go back maybe to the definition of A tensor algebra B?
This one?
Mm-hmm. Okay. Okay, thank you.
So can I go back now?
Mm-hmm. Thanks.
Okay. Now, this definition satisfies some nice properties, which we will use later, which they basically say that, first of all, if we have a star homomorphisms between pairs of algebras, then we can consider the minimal tensor product of these two homomorphisms, these two star homomorphisms, acting from the minimal tensor product of A1 and B1 to the minimal tensor product of A2 and B2, such that it behaves in a way we would expect it to behave on the algebraic tensor product. So basically, it just says that we can consider there is a reasonable construction which we can call the minimal tensor product of star homomorphisms. And the next proposition, which actually will be needed to us, is that the same can be done for UCP maps, but here the UCP maps are already not between arbitrary sister algebras, but rather from some algebra A to some algebra of bounded operators, and the same for B. And we have UCPs like this, then what the next proposition says is that we also can consider the minimal tensor product of the corresponding UCPs. Okay, any questions?
So is it clear, or are you going to prove it, or are you not going to prove it?
Actually, I mean, I could elaborate on the, actually it depends on your preferences.
Depends if it's
maybe
interesting.
say something.
Okay, sure. So I will not go too much into details, but like the idea of the proof yeah, the idea of the proof for the first one is that first of all, if we have first of all, it is not that hard to construct a map like this, because of the universal property of the algebraic tensor product, namely, we consider a map like this, which just like
Yeah, this is the input that you gave in the proposition, right? A map from A1 to A2 and from B2 to B1 to B2.
So we just consider such a star homomorphism, which I don't know, which behaves like only to the, which maps only to the first component and behaves exactly like PA, and we do the same for on the first component, and we consider the same from B1 to the minimal tensor product, which behaves only on the second component. And since they behave to the different, since they map to the different components of the tensor product, these ranges are definitely commuting. So we can glue them to a map, to a star homomorphism P like this, and like the only thing which remains to be checked is that this P is actually continuous, so that we could lift it to the map from the completion, that it is continuous in the minimal norm, so that we could lift it to the map from the completion, which will be exactly the minimal tensor product of A1 and B1, but it will be, this one is already kind of long and boring, so I'd rather skip it. This is about the first proposition, and for the second proposition, I'll remind you of the statement just in case we are now dealing with, we want to say the same about UCPs mapping to the operator algebras, and I remind you that by definition, a UCP is just a compression. By definition, a UCP is just a compression of a homomorphism. So we have some homomorphisms which give our UCP maps. and by the first proposition about star homomorphisms, there is a we can consider the minimal tensor product of the PA and PB, and like this will be the map from the minimal tensor product of A and B to the minimal tensor product of the extended operator algebras. And what we do next, we just we can consider this minimal tensor product as a subalgebra of the tensor product of the Hilbert spaces, or the bounded operators on the tensor product, and then we compress. Then we compress it to the algebra of bounded operators on the tensor product of the smaller spaces, and this way we get the minimal tensor product of the UCP maps. Mikhail, am I supposed to finish now?
You should, if you have something small to say before we finish, maybe just tease us a bit about what is done next time, and then we will wrap it up.
Okay, this time we defined the minimal tensor product and discussed its properties a bit, which will play some role in the proof that the Kirchberg QWEP conjecture implies Tsirelson's conjecture. So after that, like after discussing this, we okay, we already discussed it, but like next time we are supposed to discuss first the maximal tensor product to discuss its properties a bit, and then to proceed to the also we will have to discuss the group sister algebra, which appears in the QWEP conjecture, and then we will proceed directly to proving that QWEP implies Tsirelson's conjecture.
Can you maybe give a little, a tiny spoiler, informal spoiler of how do you define, how do you close it differently other than taking the closure?
Yeah, this in some sense was the obvious way, right? Like,
yeah.
This one is clear. This was the one that any one of us would probably guess.
So the second, let's just go over the definition. Okay, the second definition is more universal. So that it would look more natural, I'll remind you that if you have any homomorphism between sister algebras, like I don't know, let's X and Y be sister algebras, P be pi be star homomorphism, then it's a well-known fact that it's non-expanding. It cannot expand the norm.
Yeah, Alon mentioned it.
Yeah. I'll just recall it. And so, given this fact, the following definition should appear much more natural. So what we actually do is we consider all star homomorphisms from the algebraic tensor product to all possible algebras, to all possible operator algebras on all the possible Hilbert spaces. And we know that once we endow the algebraic tensor product by a C-star norm, it should be non-expanding. So like, if we think about it like this, the most natural thing to do is just to define a norm of an element as the supremum of norms of images over all such star homomorphisms.
The max
It's not clear that this is well defined, but
yeah, well, supremum.
Yeah, it is.
Yeah,
It is not clear that this supremum is finite. It requires some proof, yeah.
So the maximum is the supremum over all star homomorphisms, and the minimum is what? Which norm?
Using a specific representation, you take you have HA and you have HB, right? In my talk, we talked about that you can take tensor of Hilbert spaces and get a new Hilbert space. So the algebraic tensor product acts naturally on this tensor product of Hilbert spaces. So you have a representation and you just take the closure with respect to this one. So this takes a very natural representation.
Okay, so one of them is just with respect to the norm. There are two different norms. The completion with respect to two different norms, the minimum and the max.
Yes.
Okay. Is it clear that this is really a minimum?
So that is actually a theorem. It's a theorem of Takesaki. It's pretty clear that the maximal norm is the maximum you can get because of its universal definition.
It's defined with the maximum inside, but
yeah. However, the minimal, as you remarked now, it's not so clear that it's the smallest one, but that is true. So as I said, like, these questions are really subtle. Like, you defined it in some sense, and why is it minimal? Then it requires a proof. Why even it's independent of a presentation, it requires a proof.
Danil, can you go back to the slide that actually writes down the Kirchberg? I forget the letters.
QWEP.
Okay.
QWEP. Okay, this thing. Sorry, Alon, I didn't mean to disturb.
No, I wasn't saying anything important.
What C-star F2 stands for, we haven't defined yet.
Okay, so Alon, the definition
but at least we have a flavor of it. It's taking the group ring, defining again some kind of a norm on the group ring, and then taking the closure of it with respect to this norm. So in some sense, the main idea of what the C-star F2 is, we just need to define the norm, but it's taking the group ring of F2 and then closing it with respect to some natural norm that can be defined on it.
So Alon, when you said that it's a theorem, you meant that the norm that we just discussed, the natural tensor, the norm that comes from the natural tensor product, gives us here the minimal object.
Exactly. Like, because of how Danil defined it, the maximal one is a universal object, you can see that the right-hand side is a quotient or a factor of the left-hand side, right? So it manifests itself also as saying that the maximal norm is greater than the minimal one, but it's also a theorem that any other C-star norm you take on the algebraic tensor product will be greater than the minimal one. So it will have it as a factor, but that's less clear.
More questions?
I have an understanding question, but maybe I'll ask after we've finished so that I won't.
Okay, so let's thank Danil and Alon. It was a great talk. And they will talk more about this next week. And I think next week I'll say what will happen in the rest of the semester.
was a paper of Valette who used Ramanujan graphs for this problem. Do you know about that something?
For this specific problem or something involving tensor products? Or
I don't remember. I remember that there was a paper and uses the Ramanujan graphs to answer some problems of this kind about two different tensor products. Try to look.
Yeah, I will try to look.
Many years ago, like 20 years ago, I don't remember what was exactly the paper about, but for some reason, Ramanujan graph showed up.
Interesting. I'll look for it, certainly. But yeah, like these type of questions, they are quite, their formulation is quite abstract, but they indeed like sometimes involve like more concrete objects, like for example, in this case, the Tsirelson problem, but certainly, I mean, I wouldn't be very surprised.
Yeah. Okay. Thank you.
Thank you. Thank you, everyone.
Thank you.
Thank you.
Thank you. So can I bug you with questions? So just the definition of the maximal norm,
Yeah.
it looks a bit weird that if you say that every star homomorphism is non-expanding, meaning if I understand correctly, meaning that for pi, the norm of the image cannot be greater than the norm of the thing being mapped.
Yeah.
But then if I take any star homomorphism and then I give in the definition of the maximal tensor product, and then I give it, after I have the map, I give it the minimal norm on the left-hand side, then somehow the fact that it's non-expanding needs to tell me that the norms have to agree, or the minimal has to be at least the maximal. No, so I'm saying
not continuous or
what?
What I compiled from what you said is like exactly the correct statement, no?
No. So A tensor alg B going into A tensor alg B, and then I'm saying on the right-hand side, give it the maximal, right? So, and then, yes, on this, give it the maximal, take some star homomorphism, and then give the left-hand side the minimal. So if I'm saying every star homomorphism, which doesn't have to be C star homomorphism, just star homomorphism, is non-expanding, then it must tell me that the norm, the minimal norm, has to be at least the maximal norm, which we know is not true, but
not exactly, because like if you consider any star homomorphism here, you just won't be able to extend it to a star homomorphism from the minimal tensor product to the maximal tensor product.
If I understood correctly, also,
like yeah, something should be non-continuous.
I see what you mean.
You lose, like
it's not true.
There are converging sequences on the left side that are not converging sequences on the right side. And this means that what you just defined is a it's just not continuous.
That's fine. We said star homomorphism doesn't have to be continuous.
On C-star algebras. So I didn't say it because explicitly, but the statement is only true for star homomorphisms that are defined already on a C-star algebra. But the algebraic
tensor product. But it is a C-star algebra.
The algebraic one is not. The algebraic one is not a C-star algebra. It's just a star algebra. This is what Alon means.
Yes, the whole point is that sister algebra must be complete by definition.
Yeah. Wait.
Like we are doing
So
this
saying
because
in the definition of max, I'm using a alg b, and so there are maps that I'm considering there that won't appear once I'm looking at the domain that is a slightly bigger, which is the closure, which is the minimal. Yes, do I understand correctly?
exactly.
Yeah.
Okay. Okay. Great. Thank you very much.
Yeah, but the important point is that it's the other way around. Okay, so you want to kill the least number of representations of your original algebra. You had some algebra which is just a star algebra and not a C-star algebra. You want to give it a C-star algebra structure such that you don't lose any representation. The way to do it is only by taking some norm which is larger than any possible representation. This is the only way possible to achieve such a property.
Yeah, because like
because of the contraction
you want not
condition.
to, yeah, because of every homomorphism will have to
and you are
yield
correct
for that.
It automatically means that nothing embeds in it. Like on the other hand, any other completion does not embed in this star algebra. Because you want to preserve all the representations, you lose some embedding property.
I see. Great. Thank you very much.
Thank you for the questions.
See you next week.
Okay, bye.
Bye-bye.
Bye.
Bye.